Okay, this is AI. Did that prove that the proton model is wrong? Well, it might have, but I can show you that light is made of these little dipole electrons, and those add together to make protons. Now let's see what he has to say here. He says that people are made of cells. We all have cells in us. Cells are made of molecules. Molecules, which are big forms of things, are made of tiny little atoms, which are these. Well, guess what? Atoms are made of dipole electrons. That's what atoms are made out of. And they can smash them, and they can see all this debris come out. But we actually use light itself. We use light to visualize the particles that light is made of. All right, think about this for a second, because I'm going to show you in a second. We can see what light itself is made of. When they smash these particles together and they see all this debris go, it's just a huge blinding light. Well, that's because they're made of light. Hold on a second. Okay, I'm sorry. It strikes me funny that they just can't get their head around this. All right, let's follow this. Here goes.
People are made of cells. Cells are made of molecules. Molecules are made of atoms, and atoms are made of electrons and protons and neutrons. And those last two are made up of 3 quarks.
All right, that's where they're totally wrong. The quarks they're not made out of 3 quarks. They see all kinds of debris coming out when they explode them. Let me show you what they see. All right, this is what they do at a nuclear collider. They send all these beams going one way and another way, and they're supposed to hit head on, and when they do this. And they throw off all of this stuff. What is this stuff? What is it made of? They see all the same sort of particles over and over and over and over again, but they just don't understand what they're made of, and they never ever see the dark matter. Or actually they do see it, but they just don't realize what it is, because the dark matter is involved in the electron. It's half of the electron. It's just they never saw it, because the electron is the only part that glows. The dark matter part, which is the muon, doesn't glow, it doesn't emit, it doesn't absorb, it doesn't radiate anything. This is what we started with. When we explode these, we can see these little particles quite easily. But they're always attached to a black. Well, not always. They can separate completely and go on their own, just like this. And then they will come back to the black instantly, because that's the strong nuclear force, is the black attracting the white. Okay, my friends, another shocker du jour. Electron dipole flood theory predicts all of this. LHC, Large Hadron Collider, one of the few places on Earth, can produce and collide energetic photons. Those are light particles. It's the only place scientists have seen 2 energetic photons merging and transforming into massive W bosons. So they claim that CERN's Large Hadron Collider creates matter from light. Now this goes back several years, and they've sort of dropped it because light literally is matter. Light makes up protons. Protons consist of 1,823 light particles, and I'll show you those right now. Okay, I think the easiest way to do this is to just show you a variety of interactions, and then I will break it down for you very specifically. This is light being pulsated from a red pulsed laser. Okay, and it's coming through the air, exciting all the other molecules that are in the air, all the other gases, because they have electrons. This is a particle in these waves, and now we've accelerated. Now, CERN is not the only place you can accelerate. We accelerated it just using a simple venturi. And the particle itself, which I just said, is in this wave. You can't see it, but once it starts to accelerate, it pulls itself out of the wave and literally drags the wave forward and concusses at the venturi and separates into the black and white, which is what it is made of. These are the black and white particles. That is a photon. These are photons. Now, when it comes out the venturi, if we were looking into the venturi, this is what we see. We're looking into the venturi there. We see these Higgs fields. They understand that. This is a Higgs field. These are Higgs fields. This is the blue coming through very fast. and much faster, much more energetic than the red. Now let me show you some other ones. Okay, when they see neutrinos, they do see them in a few different phases. One of them is the Dirac neutrino. It's just completely white and completely black. Then there's a variety of in between they call Majornas, and I will show you those happening right now. This is the red laser light. Remember I showed you that it was accelerating here? Well, this is the particle that was in that wave. So what is this? That is the neutrino phase. It's not fully formed into a photon yet. This is also a neutrino sideways. These would go this way and this one goes up. I don't know. I can't account for it exactly, but it is a stacking up of energy just before it concusses, and then we see the light come back at us. That's a bouncing back of light. That light is coming back at us out of here. Just like it does when I send light down on anything. I send light down on this, it bounces back. That's the only time you see the light. I don't see any light here. You don't either. So you don't see this. But once it hits here and bounces back, that's when you see this wave come back at you. Now, I just showed you the photons and the neutrinos. The same thing here with green. It's the same particle. It's only a faster spin. And this, again, is the neutrino phase just before it turns into the photon. See, this clearly demonstrates how weak the red is compared to the green. The green is just a much faster spin. And that's all it is the particles are spinning, just like this. When they went through the venturi, some went that way, some went this way. I'll show you. All right, let me explain to you. Light is a spinning particle. This just happens to be a red one. And it's slow. Red is like this. If you looked at that sideways, it looks like a wave. It looks like a flappy wave, yes. But it is not. It is spinning this way, and this proves it. This is a tiny slit of a venturi, single slit. And it's a venturi means the fields crush. When this thing spins, sometimes they go that way, sometimes they go this way. Usually they come down the center because the whole thing is flushed with these particles. So most of them end up going through the center, but some go off to that side, some go off to this side. Now red, like I said, very stretched out. Green is like down in here, and blue is like right there. And I mean, blue is very, very powerful compared to the red and the green. I think I showed you the red and the green at the same time. Which is, this is it. The green reconcusses way out here. I mean, much stronger influence than the red. And I think it's going faster than the red, but I can't prove that. And it may not be. But I can tell you one thing. Light can go all different speeds. Now, you know, I can see that well, here, let me just show you just to prove my point. Look at this blue. You see that? That's coming in from the venturi this way. If that's not slowing down, I don't know what I can say. And if this isn't speeding up, I don't know what I can say either. Hold on one second. Let's see a better speed upper. Well, this shows it better right here. There's the white wave. It starts like this. It would never gotten like that, and if we didn't use the venturi. Now the venturi says, "Come on, bring it through." And now all that white just disassociates from the black. The black. This is what's fission and fusion. Right at the venturi, we created fission and fusion. All right, here it is, right here. Whoops. The black and the white were together here. They started glow, and then when they hit the wall here, which is the venturi, the black can't get through. It just can't get through. It's too small. And the venturi has a cut to it this way, so all the fields have to crush, and they do not want to crush. It's exactly the same effect as hitting head-on. Identical, only we're making them force into a slit like this, but in order to get through that slit, they have to just crush the heck out of each other, and they do. And the black desperately wants to be reattached, and it does come back right out here. It starts to completely fill back in, and it tries to nibble in all the edges it can get to. But through here, we have strictly white energy, and that is raw electricity. I don't see why we can't harvest that and get free energy, and I don't think it's a big deal. I think we could do it with a little device, something like this, and have these little lasers in there with a receiver over here after the venturi, and all that can be made just tiny, 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 tiny. And the increase from light to the energy, if you can separate it, which is what we did, that's fission and that's fusion. And if you can do that, they say you can increase it a minimum of 200 times the energy. So if we had 5 watts here, we get 1,000 watts on this side. If we can even harvest 30% of that, that's 300 watts. From 5 watts up to 300 watts, that's not a bad increase. And you could put literally thousands of these little tiny things inside of a box not much bigger than that. Carry it around, and it would be, as far as I'm concerned, you just could tap into it. It's free energy coming out of there. The power would power itself. These are the kind of particles they're seeing, which are just all scraps and bits and pieces of like these big particles smashing together, and then they're all flying here. But what we started with was this one right here. That's light. Then the light can separate and break into these, blue or green or red or whatever, because that's the energy value. But the black one always stays black. Now, X just means there's a bunch of particles. They have no idea what that could be. It could be anything. But they also see the same particles we see, and they see some quarks here and there. I'm sorry, not quarks. Oh, man. Neutrinos, I'm sorry. Whew. All right, and this has come as a shocker, but I'm going to tell you one thing right now. Earth and you and I and everything are nothing more than a big pile of these dipole electrons. That's everything. That's 100% of the Earth is made of these particles. There is nothing but these particles. That's the only thing that makes matter. That's all we are, is these particles. All right, so that is the nature of all matter, is atomic vapor. You can send it from the sun to the Earth, and the Earth will increase in matter, because these particles are literally matter. The light is matter. And if you shine light on a stainless steel weight that weighs 1 gram, all right, and you flood that with light, which heats it up, and then you weigh it again, it will increase. It will weigh more than 1 gram. That's why whenever you have to have weights certified, they have to weigh this. They have to be the same temperature. If they're not the same temperature, they won't weigh the same. And all it is light creates temperature. When you get hit by light, you start to increase your temperature. You take the light away, you get colder. So if you have one cold weight and one hot weight, the hot weight literally is going to weigh more than the cold weight. It's just counterintuitive, but it's true. The hot weight will have more electrons in it, jammed in there right now. They're going to try to flood out of there, but they're jammed in there now, and it'll be heavier. And I know this for a fact, because I used to work with weights and measures, and they had to be the same temperature, or you could not certify them when you calibrated them. You had to calibrate them every so often and be sure that they're correct weight when somebody buys something at the supermarket. And in order to calibrate the weights, you have to bring them up to where they have a real fancy thing that it's got 2 little claws that go in like this. You put everything together and it takes it apart, and I don't know, it's got a very, very sophisticated, but you cannot weigh them until they weigh the same, until they have the same temperature. Otherwise they're just not going to weigh right. It just proves what I'm saying. Okay, so this is what we're seeing, and because we're just using light, and don't forget it's just the photons, we completely separate the black from the white. Now, the problem is with CERN and the rest of them, they're working with these kind of particles, and this is what they see. They have 2 balls of particles that we're down here using this. All right, we're down here using these. They're up here using these. They come together and they just create all this stuff. And they're just confused. They have no idea how to interpret it. They know the red sort of hangs around, but deep inside, the blue and stuff just takes off and never comes back because it's so glued to the core. And the core of every proton is dark matter. I'll show you what it looks like. Okay, this is where it gets a smidge tricky. And you say to me, Roger, what does an atom really look like? Well, let's try hydrogen. Hydrogen is supposedly one big positive core, which is the proton, and then a little electron floating out here. And I say, no, nothing like that at all. I would say this is probably pretty much what a hydrogen looks like. All the black particles will go to the center because they can push right up against each other, couldn't care less. These want to be away from each other, and they can separate. So the white particles will surround the black. That's why we've never ever seen the black. That's why they say we can't find it. Anytime you look at this, whatever bounces back is bouncing back from the white particles. The dark matter's behind it. Now, the only reason we can see it is because we have crushed the light particles inside here, because this is up at a proton level. There's supposed to be, in my interpretation, there's about 1,823 dipole electrons. So there's a black and a white of 1823, or black and red, black and blue, black and green. Now, the blue, this should really be blue. Somebody did this for me out of the graciousness of their heart, and I appreciate it, and I lost the guy's name. I can't remember who it was, but they just did this graphically so that it could sort of show what I was talking about. Now, the closest to the black will always be the blue. That's the most energetic. That's why when you put a spark to hydrogen, it explodes like crazy. Every one of these falls apart. They all fall apart. Once you disrupt the stability and you say there's no more 1823, I'm going to throw a spark in there, that's going to be another 500 or another 1,000, and everything just explodes, and it just makes an enormous explosion. Hydrogen is just amazing, and it's just way down here. It's not like plutonium or anything. It's just hydrogen just falls apart. All of these fall apart, and boy, is it an explosion. All right, so don't forget, that's the only two particles that exist. That's the white one and that's the black one. You take two of them together to make a gluon. You take two gluons to make a photon. All the rest is just a mix of these particles. And the neutrinos, leptons, I'm sorry. Well, neutrinos too. Yeah, see, neutrinos, leptons, they call them all under lepton name. They're all made out of the same two particles. Just one of them, some of them are running faster than the other ones. They're more energy. All right, I'm sure I probably confused you enough. This is the white one, that's the black one, that's all that exists. All right, let me just explain to you. They are hitting gigantic protons head on. They call it beam physicists. They're now actively studying colliding photons with one another, but they still think they got to hit them head on. You don't have to do that. They're coming up with schemes for colliding a beam of short-lived, leptons with a beam of their other antiparticles. They don't understand them, so they're just throwing out names here. If such schemes can be realized, they will provide extraordinary new opportunities for the investigation of high-energy phenomena. Now, our scheme is to put it through a venturi. They have to crush their fields. They can't do anything else to get through that venturi. And because the black particles are solid, they just keep slapping them. And I can show that actually occurring right here. Here is the black pushing the white. You see that? That's coming through the venturi. There's the black particles. They're just pushing the white. The white can go because it's magnetic. The black's just as a particle. It's just pushing. The white wants to get attracted to it. Think of it this way. This is like iron, the black. It's just like iron. And this stuff here is like magnets. It wants to be attracted to the iron. And that magnet will push other magnets away, and you'll see them go pushing away or attracting to them. But the iron doesn't react with anything else. The magnet part does. And that's what we have. We have like an iron and a magnet. And a magnet is the energetic particle inside of light. It's a magnetic particle. I just want to try to make sure I remove the confusion out of that. When I said light is like a magnetic particle, it is. the core, the dark matter, is just like iron. It's all it wants to do is attract the white ones and viciously attract them. So it's wherever the dark matter is, the white will attract. Now, why do they only form in these certain periods, these periodic charts? This is because at every sort of, I think it's about 1823, 1824, there becomes a zone of stability. And then you add another one. So that's 1824. By the time you hit helium, that's got so many protons and neutrons in it, you're already up to 7,300 and something. By the time you get up here, you're into hundreds of thousands of particles instead of 90 or something, whatever they say. Every proton is 1,823 particles, not one proton. All right, and every neutron, which they throw in a whole batch of neutrons because they don't know what else to do with it, every neutron is 1824. And helium has 2 neutrons and 2 protons. All right, so that's like 4 times 1,823. All right, so that's almost 8,000. Okay, I guess I'll leave it at that. Again, the muon and electron shower come from the muon and electron neutrino that are attached together, called a dirac. When they come in and they slam into something, this in Cherenkov radiation, it's heavy water primarily, but they disassociate. The muon goes on its way and electron turns into showers, identical to what we have right here. And if this is correct, which it does appear to be, this would be fission because the black is separated from the white. This would be fusion when they come back together. This would be raw, completely raw white energy, which is all you want to do to pump into your batteries. This is the part you want. You don't want the black. The black is where all the weight is. You don't want that. When you charge up your battery, you don't even know it gets heavier, but it gets a lot of energy because this is what's filling it up. Strictly white, non-heavy energy. It has no mass to speak of. The black has all the mass, and that's slapping that white through there. And we should be able to send it down through a venturi, through a conductor down into the batteries. But you have to have a little receiver here. I think I showed that. Well, I know I did, but let me show you one more time. This is my concept. And everybody's, I'll just do it. Well, no, I can't do it. It's going to take a little bit of engineering. You have to engineer the venturi, correctly. And then you can do all kinds of stuff with the venturi. It can be made in a whole variety of ways. Then you have to take the laser and decide how many pulsations a second you want to have. What's the best slap? Because every time you go boom, 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 there's a whole wall of black coming out. Bam, bam, bam. And that's what pushes that white down into the batteries. Then we take a little bit of that back to the laser and just keep it running. So you shouldn't have to ever pay for electricity again if this works. And this should be able to be determined whether it will work or not within a few days. Because somebody with the technical ability and a little workshop and a milling machine, a couple little things you're going to need, and you should be able to determine, can we increase the energy? Say it takes 5 watts of energy to make this laser work. That's a certain amount of energy. If we can get back a couple of 100 watts, which is the luminosity. Luminosity tells you how much energy you have, and that's watts are energy, and luminosity is watts, and that's what we did. We turned it from that into that. So we should be able to increase it a whole lot, and then we pump it down into batteries. So, I don't know what else I can do. I've been trying to present this to the people that are the physicists that I would think they'd want to at least look at that. I mean, this is light. This is lasers. This is not CGI stuff I'm just making up. That's a laser coming through the air. And it's just starting to accelerate. And then as it accelerates, it does this. The particle shows up. Then the particle breaks off. And all we have is white and it comes back together. I see that as fission and fusion. I don't know if you do or not. And this is from Fermilab. They see the particles. There's the same article. Shows those 2 particles. And they say one of them has no mass, this one, and this one has all the mass, it's a fixed particle. And I show that's all exactly what they claim, and I agree. So anyway, hopefully someone will contact me, and we see if we can move this thing forward. But I cannot do it. All I ever is, if it's so easy, why don't you just do it? Well, I can't do it. First of all, I don't need to do this. This is not for me. I got enough money to buy my electricity. This is not going to do much for me, trust me. But I find it very interesting.